Determination of analyte amounts. We like to call this kind of analysis quantitative analyses. Why doesn't that work? Quantitative analyses. Okay. So it's really nice, Andrew, when things fall into the equation of a straight line, our data. Like usually, well, let's see if you can tell me. What is, I guess you'd have y here and x down here, right? But what's the little m and the little b?
M is going to be your slope.
M is your slope. And b, everybody, is y-intercept. Okay. So these are just numbers, right, Brad? These are just numbers. Where do you get these numbers? Where do you get them? Yeah, where do you get them? Because there's just supposed to be numbers. I guess the full story.
By finding derivative of your points.
By the full story. Like y is usually your signal, right? Pick it. Current, absorption, whatever, right? And x, since we're talking about quantitative analyses, x is going to be your concentration, right? So you're plotting your concentration, and then you're just getting different signals for it. And then the idea is you put your unknown in, and its signal is right here. So you go across on the plot, come down, there's my unknown concentration. I figured it out. But I guess what I'm driving at is nobody does this. No one, people will get mad if you did do that. I would get mad if you did do that. Because you're not supposed to do that. You're supposed to use the equation, right? You plug in these numbers, you know what that is, and you know what that is. And that's what I'm asking Brad about, and we'll get to it. You'll know what M and B are. You know what this is, because that's your signal for your unknown. So you have one equation with one unknown, and you solve for it. So you solve for your x, your concentration. And that's what you have to do every single time in a quantitative analysis. Okay? And then having the plot looks nice, because it shows where you're getting stuff from. But, okay, back to the M and the B. Where do you get it? All right? Let me show you. See if you remember the techno jargon here. Okay, here's some data. I plotted it out. I don't know why it did this. I'm having some technical issues, but you can kind of see the plot, the little circles going up, right? So I have absorbance is my y-axis, and on the x-axis, can I make that smaller? Yeah, the concentration of blue, okay, in molarity. I don't know why it's all down here. I wonder if I can. I'll probably screw the whole thing up, but I'm going to try. Oh, no, I can't. Can I? Ooh, I can do this. No, I won't work either. All right, whatever. So I'm going to fix that later. But what this software is called is Graphical Analysis. And if you're good at Excel, then you don't need to worry about this. But what I'm going to do is I'm going to try to get the slope and y. This is not that linear, but it's kind of linear. It'd be better if we spread it out more. But first, highlight all the points. Okay. Then I'm going to go to, I think, Analyze. Yeah, Analyze, and then Regression. And it's different in Excel. And there pops up this regression box. And there's my slope, 0.657. There's my little m, and there's my little y-intercept, negative 1.6297. So those are the two numbers that you need to do this analysis. You measure your unknown, and let's say the absorbance is 2.5. Well, you plug in 2.5 for y. You know what your m is, your y-intercept. Solve for the concentration. Okay. So that's called a regression equation when you write it all out, or regression analysis. We're not going to use this too much, because to know what the error is, you need to know what the true value is. And Usually don't, right? So you're trying to report what you think the true answer is, but just in case we do need it. And it's kind of insightful. You have the absolute error, x bar minus xt. What's x bar, Shelby? The mean or the average? How about xt, Eric? Usually t is time, but not in this case. No. Standard deviation is usually a little s or something. Think of it as error. This is your answer. And you're subtracting out, finding the difference between your answer and the true. Little xt is the true. So you hardly ever know it. But it's, you don't get the exact right answer because there must be some error, right? Assuming you did everything right, that error could either be ER, an R-type error, and S-type error. You sum up these two errors. What are the two types of error? Kevin, what are the two types of error? It starts with an R and it starts with an S. Random error and systematic error. Okay, which one of these, Kevin, can I hit you on the back of the head for and say, you're screwing up with this machine? Systematic, right? It's always too high, always too low. Systematic, something's off. You're doing something wrong. Random is, you don't have much control over it, right? It's all over the place. But it's equally above and equally below. Percent relative error, same type of idea, just different way of expressing the error. But either one, you got to know the true value, okay, which doesn't often happen. What does a calibration curve represent? Does a calibration curve have to be linear? Here's a calibration curve. Does it have to be linear? Eustacio, what do you think? Does it have to be linear? No, it doesn't. It's sure a heck of a lot easier if it is, though, right? Because then you can use this. Imagine if it's not linear. Plot one out. Signal, concentration. Make one that's not linear, however you want to draw it here. Right? So if it's not linear, do 4 data points characterize this curve? I mean, I got them pretty well spaced, but usually you don't get that lucky in spacing them, right? Usually something like this guy's missing, or, right? So you need a lot of data points. And that's, Eustacio's right, it's going to be a hell of a lot of work. Look at all the data points you need to characterize it. But one thing that's important, that'll catch you, is regardless of the type of calibration curve, whether it's nonlinear or whether it's linear, you're only good for this analysis with the highest and lowest concentration. Otherwise, you can't even use it. It doesn't matter whether it's linear or not. So the signal range for this linear plot is only right here. If you're outside that signal range, you have to make a bigger calibration curve, okay? Because you don't know. You don't know if it's linear outside those because you haven't tested it. Same with this curvy calibration curve. Limit here, and I guess I got to extend it somewhere around here, right? This signal is the only region that it's good in. Otherwise, you need more data points, okay? Dynamic range. We're getting into some jargon for salesmen trying to sell you an instrument, but it's also when you're trying to use something. Dynamic range. Which type is easier in the first place, Shelby? Calibration curve? Linear or nonlinear? Linear. So dynamic range refers to linear. You want instruments that have a huge dynamic range. Ooh, great, great. But Andrew, what does that mean? The UV-Vis, they told me, has an order of magnitude of 50 or something dynamic range. No, sorry, 5. It's an order of 5. What the hell? Dynamic range. And it has something to do with linear.
So just like each point moves too much to make it, if it makes it nonlinear?
You're getting there.
When you start getting values that don't give you a linear.
Yeah, when you get values that are no longer linear, right, along that curve, you're out of your dynamic range. So dynamic range is just the linear range. When we made this plot right here, we just made data points from here to here. I assume the little area just above and the little area just below, that's still linear. That should be still in the dynamic range, but you don't know. But way out here, you know, how do you know, right? The dude tells you, the books and the manuals tell you dynamic range, but you can't trust it. You gotta, you know, make your calibration curves bigger. What is an easy way to tell if you're still operating within your dynamic range? And that's a big deal because you want to stick to using this equation. Otherwise, you need so many data points. How do you know if you're still within your dynamic range? Brad and some other people are doing the UV vis. And let's just pretend they're doing the analysis of this blue compound and they want to see what the concentration is. And they made all their little lab and they got it all done. And then they flip it over and then the page says, okay, now pull open the drawer and analyze this one. And it's super dark, right? So how do you know if you can use the same equation or not? There's an easy way. At least this is what I say is an easy way to tell. If you double the concentration of something, should the signal perfectly double if you're in the dynamic range? Yeah. So if you triple the concentration, the signal should triple. If you have it, it should halve. It's that idea. So you make up a really make one that's really just as dark, put it in the machine, and if it's 10 times as concentrated as as one of your standards, its signal should be 10 times as high. And if it is, you can analyze it. Yeah, it's doable. Otherwise, if it's not, oh shit. Look at all the data points you'd have to get. It'd be horrible. So I guess what I'm trying to say is, dynamic range means it's linear relationship between your signal and your concentration. And if you double one, the other one has to double too. You triple it, if you have it, it has to be consistent. That's what a linear relationship is. 3 types of external standard calibration curves. Okay, you're actually going to do this in one of the labs. I forget which one. You're going to do each one of these. Let's see which one's the best. Single point calibration curve. So again, on all these calibration curves, on every single axis, you can write signal and concentration. They all have to look like that. No matter what the technique is, right? They're all signal and concentration. Okay. But single point means this is all you have. Sometimes it's easier to look at the table, right? Because you have to make this data table. And all you have is one of them. You only have one thing to plot, so you plot it. Okay? Well, how the heck can you get an answer out of one data point? Now, you had to make this standard. This is the standard. This isn't your unknown. You had to make this standard, because these are what you plot in calibration curves are the standards that you make. Typically with, MIVI equals MFVF or something, right? A dilution equation. So what they say here, you calculate a K. You calculate a response factor. K. And K is just your signal all over your concentration. And the book likes to have these little A's. I guess the A is for, what do you call the compound that you're looking for all the time? Analyte. So the signal of the analyte divided by the concentration of the analyte. So this is my signal of my analyte and the concentration of my analyte. So you calculate your response factor, K. Then what you do, all right, then measure SA of unknown. And use K to find the concentration of your unknown. That makes sense? Because you know what, right? Because concentration would be what? SA over K. And you already found K. That's from up here. And your signal, that's the signal for your unknown. So you just divide the two and you'll have your, it's a rough estimate. But it really works good on the GC. I'm not sure why. But sometimes you get better answers with this. I think it's just because you're introducing more error when you do more measurements. And I see that, that's why I do a lot of things I do that's kind of weird and analytical. Let's skip this step. Let's not do this. Let's keep all this, let's just, everybody use the same jug of water, not degas it. The less steps you introduce, the less error you're going to have. So this is a good example of that. If you're a newbie to the using instruments, very often, because the odds of doing it once really well, I guess, is better than getting overall good results doing it 4 times. If you're a noob. Multi-point calibration curve using external standards. So pretty much the same thing. Got to get a lot more data though. Make a whole bunch of standards. Like 4 or 5 or so, right? Measure their concentrations of those standards, whatever your analyte is, and then plot them out. Okay. And then we'll get the data. We'll plot it out. And I guess plotting out and get the regression equation, right? That's what you really need. Get the regression equation, right? Then you can calculate your concentrations. I guess I could write CA. Calculate your concentrations of your unknowns. So when I say get the regression equation, I'm really talking about getting what variables? Get little m and b. Get little m and b. That's all you're doing for getting the regression equation. External standards and internal standards. It looks like these two are really similar. Something's going on here. Eustacio, what's going on here? What's the difference? External standard, internal standard? All right, they're all things that you make with your analyte from, like here's a stock solution of 700 parts per million blue, whatever that is, right? And I could make whatever concentration I want. I could do MIVI equals MFVF and make whatever concentration I want. So would that be called, Kevin, an external standard or an internal standard? It's external. It's external. So pretty much every standard that you ever made in your life, external standard. You have some stock solution. Okay, you do the calculation. Okay, I want 60 ppm, and this is 700 ppm. So 60 ppm is MF, right? And I want 100 mils of it. So VF is 100 mils. And we're doing this, and then you solve for VI and take that amount and put it in here and dilute it up to the mark. So that's how you're going to make so many standards, except it's called an external standard. Okay, internal standard. Let me just show you what it's going to look like first. If we, the plot is a little bit different. Signal of your analyte over the signal of the ISTD. That stands for my internal standards. I have to write all that out. So I'm going to divide 2 signals versus concentration of my analyte. So in my data table, I have to measure 3 things for each analyte. Sorry, each standard that I make one standard. I have to know its concentration. And then I have to, on the instrument, I'm going to measure the signal of my internal standard, sorry, the signal of my analyte, and the signal of my internal standard. So that the internal standard and your analyte are two different things. But they have to behave really, really similarly for this to work. Okay? So what's the big deal here? Why are we doing this? Let's say, how can I draw a volume of a gas? Okay, let's draw a box. 2 boxes. We are going to sample a gas 2 times. Here's the first time, and here's the second time. Okay? So, I don't know. We sampled the gas. The first time, we get this. Sample the gas the second time. Get this. Okay? And it's really hard to get the exact same amount of gas every time, because gases are tough, right? They're so going all over the place. So it's really hard. Sampling fluctuations, the terminology is sampling fluctuation is really high with gases. Well, which instrument do we have measures gases? GC. Its life depends on it. It's got to reproducibly sample the same amount of gas each time. Because just think of this. If you're going to make a calibration curve with all these different concentrations, you better be sampling the exact same amount of gas every time. Otherwise, all your results are thrown off. Well, the instrument can't do it. It can't sample the exact amount of gas every time. So what do? You throw in an internal standard, some compound that reacts very similarly to your analyte. So my little stars are my analyte, and let's make little dots or something for the internal standard. Make them green. It's internal standard. And then, so that's sampling so this internal standard is put, in the solution. So you just put some in there, and you analyze it once. Analyze it a second time, you should get, we sampled more gas in the second one, right? The instrument somehow, the fluctuation, it sampled more gas. Well, if it sampled more analyte, it's also going to sample more internal standard. Right? It'll sample more. I should make these more mixed up, but okay. So what I'm trying to drive at is, if you did not divide by internal standard, you would have been way off. But if you divide by the ratio didn't change. Well, it's really, really similar. Because if you sampled more analyte, you also sampled more internal standard. So even if you sample fluctuations, they don't really matter with internal standards, because that increase that you sampled, even if you sampled too much or too less, well, the ratio now is going to be smaller or bigger, and take it into account. So that's why they do it. And then with the GC, you're supposed to get much more linear data. Okay. So we'll make, since there isn't a whole lot of homework, we'll just make this one homework. Okay. So pretty much just use Excel or Graphical Analysis. I can give you that because we've got a site license for it. Okay. But I think Excel is pretty nice. So you pretty much plot everything out, right, and get your regression equation. Okay. So because here's the unknown signal. So plot everything out, get the regression equation, get your little M and B, then use this signal. There's your SA of your unknown, right, to calculate the concentration of your unknown. Okay. Standard addition technique. Sample matrix. I think we talked about this in analytical. Maybe not. Did we? Matrix. Does it sound familiar? What was it? The chemical, perfect. The chemical environment of your analyte. Whatever's chemically around it. Okay? So what is an external standard calibration curve? What is an external standard calibration curve? Is that just this stuff? Yeah, this is all this stuff is external standard calibration curve. Except the only one that isn't, I guess, you would call this one internal standard calibration curve. And then all of those well, let's ask this question first, I guess. When will an external standard calibration curve give incorrect results? And it's nothing to do with what you did. You made the solutions perfect. You did the analysis perfect. But your results are way, way off. What could be an example of that? You pretty much have to think of how an analysis works. Like, let's say if you're going to figure out how much caffeine is in Coca-Cola, okay, and maybe caffeine absorbs at, I don't know, I'll just make up a number, 235 nanometers, absorbed really well. So that's where you set up your detector, 235 nanometers. So you make up your standards, you have some stock solution with caffeine in it, and you make up all these different concentrations of caffeine, and you run them in the machine, and you make your nice, beautiful calibration curve, right? And then you take your Coca-Cola, and you inject it, and you get your nice signal, and then you find it on the calibration curve. Ooh, here's the amount of caffeine. You're so far off, right? And then all your bosses, whoever, get all pissed off. How could you have screwed up? It's caffeine. It's 235 nanometers. That's what caffeine absorbs. The reason why this stuff is working so nice and everything in your life has been working so nice up to this point is this has been our solvent. Nice, pure water or nice, pure ethanol or whatever. Now your matrix is going to be, I don't know, that. What the hell is this, right? Coca-Cola is not a pure compound. There's something else in there that absorbed at 235 nanometers. There had to be to throw your results off. That's the only thing I can say, is that if you got the wrong answer, it's your sample matrix. Something in there is interfering with your signal. It's enhancing it, or it's decreasing it. Maybe it's interacting with the caffeine and it's just sucking it up. So how do you, if that's the problem, how do you fix it? What you could do is you could perfectly reproduce Coca-Cola and use that as your solvent, right? Because then it would work. Because then your sample matrix is the same in all these standards. Your sample matrix is perfect when you make your calibration curve. It's the same as in your unknown. That's really what the trick is. Make the sample matrix the same in your standards and your unknown. Then there's no way you can screw up. But jeez, to analyze Coca-Cola and to make it seems kind of ridiculous.
Could you dilute it?
So you could that's the way to think about it. If you dilute it, those matrix effects should decrease, right? Because then you're going to make it more and more and more like water, right? That's a good solution, okay? I like that one. That's exact right thinking, okay? But, I don't know. Let's say you don't want to dilute it, or you just want to use something that's always going to work. Standard addition technique always works. You don't have to worry about what the matrix is. Okay? Why? Because the matrix is your unknown. You just spike your unknown. It's pretty much what you're doing for standard addition technique. So how is it done? Well, let's answer this question first. When should the standard addition technique be used? When this isn't your matrix, right? When you can't easily reproduce the matrix. If you can't easily reproduce the sample matrix, just do standard addition techniques. Life is so much easier. Okay. So how is it done? So that's what I have all this stuff up here for. Well, here's a good example before we do it. I worked for Koch Industries for a while, and I forget what the heck I was analyzing, but this guy told me this story, and it's stuck in my head ever since. I said, you know, why this analysis would be so much easier if we didn't do this. We just ran it Because I have all these nice standards here. I'm all ready to go. Why do I have to go do the standardization technique, right? Because look how clean this stuff is. He says no, because those guys that give us these samples were all coming from, some big pit. The quarry is what we're going to analyze. Actually, solids. And he said those guys. He visited them once, and he said they were pissing on your samples. They're spitting in them. he said that's what they do because they're so bored. So you can't just make these nice clean standards and expect it to work. So here, this would work. This is what I did is this is the analyte mixed in pure water. Here's our standard, and we could make these external standard calibration curves. Everything's going to work hunky-dory, beautiful. Everything that you've ever done before in lab, great. But if I do this, right, and get it all spurred up, and who knows what do to this thing, forget it. But you can still analyze it because look at all the sample you have. You have a lot. Just get it really well stirred up. Okay? So now what you do is you get your 4 flasks, which are right here. Okay? And if your sample, if it's pretty dilute, pretty trace, you know it's a weak signal, you want to use a lot of this. Okay? But you want to put the exact same amount in every one of these flasks. So these are 100 ml flasks, so I would probably dump, I don't know, probably at least 75 or so in there. Use a lot. So I'd dump exactly 75 in every single one of these. Okay, so now I'm pretty much done with this, my unknown, since I had a lot of it. Okay, now what I'm going to do is I'm going to spike them with different volumes of my analyte. And I know this is 700 parts per million. So I'm going to spike this one with 0. I'm going to spike this one. Remember, I have 25 mils to play with, so probably 5 mils, 10 mils, and 15 mils, right, of this stock. Then, since it's mostly water, get some pure water. I'm going to dilute it up to the mark with pure water. So I was all pretty close to the mark at the end here. So I'm not really, there isn't really 2 different amounts of pure water in each one of these, but so it should be okay. So the sample matrix is almost identical. It essentially is identical in all of these. Mix them up really good. Okay. Then you plot it out. Now what do you plot out? You have to plot your signal that you get for all these flasks. Right? Remember I added, I call these flasks 1, 2, 3, 4. But in this one I didn't add any. I put 0 mils of stock. They call that VS, the volume of the stock. Here I put in, I don't know, 5 mils or something of VS, 10 mils, and 15 mils, I think I said. So you plot your signal versus the volume of your stock that you added in each one of these. So I've got 4, so I'll have 4 data points. One of them was 0, right? If I didn't add any stock, didn't add any analyte, I still have a signal because there's analyte in there. Right? And there's all this other interfering stuff too. So it's not 0, even though I didn't add anything. And it just goes up from there because I'm adding more and more analyte. Hopefully nice and linear. Okay. And conceptually, your answer is really this x-intercept. It's really right here. The volume of stock, the amount of analyte that's in your unknown, that's in here, is really equivalent to this volume of stock of my standard. But I don't know if that really helps you or not. But you just calculate it. Where is it? Here it is. It's up there. Calculate the concentration in your unknown. Again, B and M are what? Intercept and slope. So you're going to have to use it, get a regression equation for this. Okay. CS is the concentration of my stock solution. So you need that. And you saw me. I took like 5, I don't know, right? I took like 5, I took different volumes of stock of this. So that's 700 parts per million is the number I would use. And Vx, what do you think Vx is? The volume of the unknown that I put in here, right? I think I said I put 75 or something, right? So I put 70. It was the volume of that unknown that I put in each one of these flasks. So if it's 75, I put in 75. If I only put in 1 mil in each one, it'd be 1 mil. So it's just the volume of the unknown that I put in there. Then you calculate it. It works pretty slick. That's it. That's all I have. So have a good weekend. Have some